Hello, Professor Barbara and fellow CS 584 classmates. I'm Ed Corlett, and my final project was on classifying letter images. The objective of this final project was to expand upon the image classification work that we did in homework number 2, where we built artificial neural network models to classify handwritten digit images into 10 classes, in classes 0 through 9. For this project, I'm using the extended MNIST dataset of letters versus the digits that we used previously. And this letters dataset includes 145,000 images in 26 classes versus the 60,000 images in 10 classes that we used before. At the end, I'll compare the performance of the similar models between the two datasets. The dataset, as I mentioned, was the extended MNIST repository. According to the website, it enables more challenging classification tasks. Images are handwritten letter images derived from the NIST special database, converted into 28 by 28 pixel images, and two examples of those images you can see here. The MNIST dataset is accessible via this pypi.org website. It's got Python wrapped around the data and to enable some convenient methods for extracting and manipulating the data from directly within Python. You just import the list datasets or different libraries for extracting the training and the test samples, like you can see here. For instance, if you just run the extract training samples with the letters parameter, you get two different arrays, xtrain and ytrain, for example here for the training image data and the associated labels. And you can see here there are 124,000 rows of data. In the approach, just like in homework 2, I'm going to implement Keras sequential models for ANN, starting with a basic model and then adding some regularization techniques. For the regularization techniques, the first one was L2 regularization, where we apply a penalty to the loss function to help keep from overfitting to the training data. 3 different hyperparameters for the loss function were used, as shown here, 0.01, 0.001, and 0.0001. The next regularization technique I used was dropout, and I had 2 different versions of that. Both times for the input layer, we dropped out 10% of the nodes. And in the first one, we dropped out 50% of the second hidden layer nodes. And in the second version of dropout, we dropped out 30% of the second hidden layer nodes. And then the third technique was early stopping, and we tried 2 different patience parameters there. Patience of 0, meaning as soon as an epoch showed no improvement in accuracy, the training stopped. So we had 0 patience. But then in the third patience equal 3 version, we allowed it to have 3 successive epochs with no improvement before we stopped the training. And the results. The basic model came in with 91.38% accuracy, and the subsequent 7 models with different regularization techniques failed to improve upon that. The early stopping with 0 patience came close, but they were all not far off, but none of them made any improvement. Here's the confusion matrix that goes along with that. You may notice right around here where my cursor is, there's 175 misclassifications here and 228 here. It might be easier to notice here in this heat map. These 2 purple squares were misclassifications, and if you count them over, that equates to the letter I and the letter L. And it's kind of intuitive to see that lowercase I and lowercase l are very similar when you write them by hand. So those were the areas where most of the misclassifications occurred. So how did the letters analysis compare to the digits? Well, in homework 2, when I ran the dropout with rates 1.1 and 0.3 on the digits data, came up with an accuracy of 98.6%. And as I mentioned, the best we could do with the letters with these same techniques was 91.3. And none of these regularization techniques improved upon the basic model. Why is this? I suspect just the bigger data set, the images are more complex, there's more letters than numbers and more handwritten variations and more classes. That's my presentation, and I hope you enjoyed it. Thank you.